Okay, so in this video, I want to talk about an application of Taylor series that's a little bit more tangible than me trying to say, hey, this is a useful theory. So we know we have a lot of computer scientists in our class. So I wanted to pick an example that's more relevant to computer scientists. And maybe one of these topics is numerical analysis. So the thing with computers is that it's not a continuous computing machine, right? So everything has to come down to ones and zeros, which is a discrete thing. And there's a finite precision to any type of computation. There's a limited number of digits you can carry. Um, and there's no limit button that a computer pushes to compute limits. So in that setting, if you want to solve a problem that involves differentiating something, you might have to approximate the derivative of something. Let's look at how we might have done before knowing Taylor series, and then after knowing Taylor series, there's a much better way to approach this problem. Okay, so recall that the derivative looks like this, right? So in our Calc 1 class, we learned that this is the definition of the derivative. It's a limit as h goes to 0 of f of x plus h minus f of x, all divided by h. So this is called the limit of the difference quotient. Basically, you've seen this picture before. So if I wanted to compute the derivative at x, I look at a nearby point at x plus h and look at a secant line passing through both of those points. And as long as h is small, that's close enough to the derivative is the idea. So let's see what the error for this kind of approximation is if we have to pick an h that's not going towards 0. So we're picking an h that's close to 0, but not quite 0. So we know how this function looks like using Taylor series. So if you plug in a point x plus h into the Taylor series formula, this is what we get. So f of x plus f prime of x times, here I have x plus h minus x, but x cancels out and we just have h here. And then the second order term, third order term, and so on. Okay, so this is what we would get if you plug in x plus h into the Taylor series formula. Okay, so let's take this expression and see what happens to this difference quotient. So you have this expression and we're subtracting f of x from it. So this is what I want to compute. I take the f of x plus h and subtract f of x from it, and then I divide by h. Okay, when we subtract by f of x, this portion cancels out. And notice that all the remaining terms have at least one power of h. So here's, I have h squared, h cubed, and so on. So if I divide every term by h, that's basically reducing the exponent of h by 1, term by term. And what we're left is f prime of x, which is what we have here, plus f double prime over 2 times h, and so on. Okay. So remember, this thing is supposed to approximate f prime of x. So if we computed this difference quotient with some h that's not going towards 0, this is what we actually compute. And this is what we wanted, right? This is an error, and actually everything else after the first term is an error, but one error is much bigger than the others, and that's the very second term right here. The reason why I say that this is bigger than everything else, notice the exponent of h, and h is supposed to be a really tiny number, right? Like 0.001 or something. H squared is much, much smaller, because if you square a small number, you get a really tiny number. And then all the other terms is h cubed, h to the fourth, and so on. All of those are much, much smaller than this expression right here. So this is the bulk of the error. Okay, so basically, if we compute the difference quotient where h isn't going towards 0, the error you have is some constant times h. Okay. All right. So this is how you might have computed an approximation of a derivative. Okay. But now that we have this Taylor series, why don't we fiddle with this formula and see if we can get something better? And there is something better, and that's called this is a balanced difference quotient. So here's the picture, and I want the derivative at x. The way to look at balanced difference quotient is you take 2 points equally spaced to the right and the left. So you're looking at x plus h and x minus h. And now you're looking at a secant line passing through both of those points. So it's almost the same amount of work as this. You still have to compute f. You still have to subtract. You still have to divide by something. But it turns out that the error of this guy is much better. Let's see how Taylor series tells us that. So we have f of x plus h. That's given by this. We already computed this earlier. I'm just copying that again. And we also have a f of x minus h here. So let me plug that in there. It's basically the exact same formula, except if I plug in negative h into the h, the odd power of h will have a negative sign in front. The even power will still be positive, because if you raise anything to an even power, it's going to be a positive number. Okay, now let's compute the difference quotient. Sorry, the balanced difference quotient. So this is what I want to compute now. I have the Taylor series here and the Taylor series here, and see what cancels. So f of x definitely cancels. The next term does not cancel because this guy is positive right here. And this guy has a negative sign in front, but there's actually another negative sign in front. So if I distribute the negative sign, this will be plus. We're adding the two things together. The next term is going to cancel because of the plus sign in front. There's another negative sign, so they will cancel. And the next term will add up together because there's an extra negative sign here, and so on. So this is going to cancel all the even terms and double up all the odd terms. Okay. And then after everything, we're dividing by 2h. Well, there's 2 copies of this. So that cancels out the 2. And there's a h that cancels with the h below. So you just get f prime from the first non-zero term. And for the next set, again, you'll get 2 copies of the same thing, and then you'll cancel out the h, so one of the powers is canceled. And this is what you get. And I haven't written out, but if you written out the h to the 5th term, this is what we would get in the end. You get all the even powers of h. And now you see what the error is. So again, this is going to be the error. F prime is what we want, and these things are much smaller, so you don't really care about that too much. Remember, the largest error is now has the term h squared in it instead of h. So if h is like 0.001, when you square it, it's much smaller. So the error should be smaller for a small value of h. Let's actually see this in practice. Okay, so let's approximate the derivative of sine function at x equals to 1 with the usual difference quotient that we use in Calc 1 class. If you type this into the calculator, this is the value I got, 0.5360 and so on. If you do the balanced difference quotient, now I'm evaluating sine at 1.01 and 0.99, I guess. And you divide by 0.02. And this is what we get for the derivative. The true answer is, of course, derivative of sine is cosine. So cosine of 1 is the true answer. And that's what the calculator gives. If you compare the error here, it's quite a bit different. So if we use the h of 0.01, the error for the usual difference quotient is 0.004. And the error for the balanced equation is 0.000009, right? So here we have 2 0 signs here after the decimal point, and here we have 5. And this isn't just a coincidence. This is pretty much what happens. Basically, we're replacing h with h squared. So you usually end up doubling the digits of accuracy just by using this balanced version of the form. That's a really simple change in computation, and it really has a significant effect in reducing the error. I'm not going to go into it here, but if you want a little bit more complicated formula for the derivative, you can be clever about how to choose the h and where you evaluate the function, and then get much smaller error as well. But that's a topic for numerical analysis course. I'm just giving you a taste of just by knowing the Taylor series, you can be much smarter about being able to compute things. Okay, I hope you found this a cool application. And this is where we're going to conclude our class. So next week, we have a holiday, Memorial Day. And after that, I think I want you to focus on kind of reviewing the material for everything we covered so far. So I'm going to post a practice final and a solution. So please use next week to review before the finals week. Okay, I'll see you guys then.